All right, just to remind ourselves where we're trying to go is where I want to prove these statements. I want to show how the connection on a manifold that models space-time is completely determined by the metric and under what conditions that's done. Now, the typical way this is shown in general relativity books is through a method, a calculus of variations method. And I'm just not going to do that because it's so common. I'm trying to get there using an alternative way to show that some simple mathematical demands can also get us to this statement here. There's the physical intuition that is shown in almost every general relativity textbook, which is basically the idea that your path through space-time should be extremal. It's a least action analysis. It's very, very common and it's not very difficult. Although the math can sometimes get a little bit awkward if you're not really good with the comp notation of tensors, which by now I think everybody here understands if you've made it this far. But I want to be able to show that you can get this just through sheer mathematical reasoning on the model manifold itself and what the stipulations mathematically are that get us to this point. And we're almost there. We've mastered some basic premises or basic expressions from in the CFREE notation, and now we're going to just get a few more and start pushing towards getting a derivation of this formula. It's worth the trouble. The next thing we do have to show is I want to show that the contraction operation commutes with the process of taking a derivative in the covariant derivative in a certain direction. This is a process, right? And remember in the comp notation that would be x alpha partial alpha, and then you would have you're taking the covariant derivative of some other vector beta like that. And you'll notice this ends up being a vector, right? This is a vector because normally this alpha y beta, which is also written y beta double bar alpha, or in more common textbook parlance that I don't like to use just because I don't like English, so I don't like semicolons. I never understood how to use a semicolon in English, so when I see it here, it just gets me nervous. So I've switched to this double bar notation. We'll erase all signs of that semicolon. So, but I want to show that contraction commutes with this operation. Contraction commutes with this operation of taking the covariant derivative in a direction of a vector x. So to begin this, we have to kind of understand how contraction is written in CFREE notation, right? In regular notation, in regular comp notation, we would say the contraction of a tensor alpha beta just equals x alpha alpha, right? But now we have to do something like the contraction operator on a tensor x tensor product alpha, right? You're always going to need, you can only do the contraction if you have a tensor, a PQ rank tensor with neither P nor Q or 0, right? That's what this would be. This would be a 1-1 tensor, for example. So the same 1-1 tensor might look like this. It's just a tensor product, right, of a vector and a covector. And that contraction literally equals alpha, the dual space mapping of alpha on x. Right, so that's the CFREE idea of a contraction of x and alpha. Now, it's a little bit ambiguous if I wanted to write a contraction of a more complex tensor where I might have x tensor product y, tensor product z, tensor product alpha, tensor product beta, tensor product gamma, where these are covectors and these are vectors. Right? Then I have to specify which contraction I want. The full contraction would be well, even the full contraction is a little bit ambiguous, right? So you have to choose which guys are contracting with which. If I wanted to contract x with beta, I might have to write a x beta operation there, in which case I would get y tensor product z tensor product alpha tensor product gamma multiplied by beta x, right, like that. So, but for this one, it's straightforward. There's only one possible way to do it because there's only one vector and one covector. And this is the basic rule for that circumstance. So now consider a tensor field x s tensor product alpha s. Now this is a tensor field along some curve. The curve is gamma. The parameterization is tau. At a certain value s, we get gamma s, which is a point on the curve in the manifold, right? It's the same thing as we always have. But in this case, I'm talking about this as a tensor field, which means it's not autoparallel. It's just a tensor field. And s is the, so, this, you could think of it as, x is a function of space-time. Let me make it neater if I'm going to do that. If the vector field is x, it's a function on space-time, which I'll note by little x, tensor product alpha, which is a function on space-time. And x is every point in the manifold. It's defined throughout the manifold, or at least in some neighborhood of some point on a manifold. It's defined continuously throughout this manifold. So it's certainly, if it's defined without the manifold, it's certainly defined on this curve, right? And so x sub s is now the value of this tensor field along this curve, but it's not necessarily the parallel propagated value, it's just the value along the curve, because we're talking about a tensor field now, a real tensor field. Now if I want to know the parallel propagated tensor relative to that field, I would write omega, say inverse s of x, say tensor product s, which is at gamma sub s. So this would be let's see how our notation works. This omega s propagates a field from 0 to s, parallel propagates a field, or parallel transports a field from 0 to s, but the inverse will take it from s to 0. So this thing is the parallel transported version of this tensor, whose value of this tensor field from s, from omega s, the point in the manifold of omega s, to the point in a manifold of omega 0, right? So that's what that symbol represents. Now, so now we can ask the question, well, what about the contraction of that, right? We've already done the contraction here of this. What about the contraction of this? Well, we use the facts that we generated in our last lesson, where I will now write that's equal to the contraction of the inverse x tensor product the inverse s parallel transport operator, right? Because we are using the rule where the parallel transport operator basically commutes with this tensor product operation. So we get this expression. But we know from this rule here that the contraction, the definition of contraction in the CFREE notation, the contraction of the tensor product of a vector and a covector is just the dual space mapping between the two. So this thing equals omega s inverse x, oops, not x, omega s inverse, okay, what did I do wrong here? This s is actually alpha, right? So omega inverse alpha, which is the covector, and omega s inverse x, and that's simply number. But we know by our other rule that the dual space mapping of parallel propagated vectors and covectors is unchanged. So we know that that equals alpha x, right? Where this guy here is clearly evaluated at 0, right? Because this is a mapping from, it would have been a mapping from 0 to s, so it's from s to 0. So these guys are here at s, and these guys are here at 0, right? So those should be the same. Wait a minute. That's not right. Sorry. That's would be alpha s x s, right? If you parallel transport them away from s, it's the same as just taking it at s, right? Okay. So what next? Oh, I didn't want to squiggle that out. Okay, so that's an important thing about the contraction that we're going to need. So now I can apply the contraction to the difference of two tensors, two specific tensors. Let's see if I can. First, I want to use. Let's see if I have. I'll just go to a different screen. I want to apply that contraction to. I want to take the contraction, and I want to apply it to this thing, x tensor product alpha, where these two things are evaluated at s, right? So I'm using this notation where I put the point of evaluation of these two, of this tensor field, this vector field, tensor product, covector field, which are functions of space-time. That's the point at space-time which I'm interested in. And I'm going to subtract from that x tensor product alpha evaluated at gamma sub 0, right? So notice how this looks. This thing here is a tensor at gamma s, and then this takes it from s to 0. So this whole thing is at gamma, is the tensor that is parallel to this field evaluated at s taken to 0 along a curve parameterized by s, right, along the curve gamma. Phew. This is that same tensor field just evaluated at gamma 0. Now notice these are not going to be the same, right? This is the parallel propagated version of this tensor field at 0 from s, parallel propagated along gamma to 0. That'll be some tensor at 0, but it won't be the same as that tensor field just evaluated at the point gamma 0. Right, so there is a difference here, and of course they're two tensors, they're in the same point on the manifold, therefore they're in the same tensor product space. That'll be the tensor product space, the 1-1 tensor product space at the manifold at gamma sub 0, right? They'll both be in that tensor product space, so you can subtract them. You could also multiply both of them by a number. So the only number that's really relevant here is the parameter value s. There's no other number in sight. And if you divide both terms by the parameter s, you can do that because they're both tensors. Right? This is a tensor, this is a tensor. It lives in tensor product space. The tensor product space is a vector space. It is a real vector space. Therefore, you can multiply any of them by scalar. So we're going to multiply it by 1 over s. And we're going to get this object that's suspiciously beginning to look like a derivative, right? So I'm going to ask myself, well, what about this contraction? This is very contrived, but you'll see that's what proofs are. Proofs are guessing where to start and ending up at the right answer. So so the contractions do commute, or I should say, contractions are linear in vector sums and products, right? The contraction of the sum is the sum of the contraction. That's a separate proof. I think we might have done it in the past. I don't know, but it's easy to show because it's just adding up numbers. You can go into the comp notation and show that pretty quickly. So we're going to then conclude that this thing equals the contraction of inverse x tensor product alpha gamma s minus the contraction. I guess I need, I should put braces here, minus the contraction of x tensor product alpha gamma 0, 1 over s, right? But we know how to evaluate these contractions, right? We're just going to use this basic rule right here, that the contraction of a vector with a tensor is just the dual space mapping between the two. So in the first case, we get 1 over s times the dual space mapping of alpha x minus but let me make sure this is clear, right? I did this, right? Back here I did this analysis, and we showed that this contraction here equals this dual space mapping evaluated at s. So, you know, we shifted from this tensor from s to 0 using this operator, but it turns out that that contraction just equals the contraction of these two evaluated at s. That's what this process showed. So when I do this, I should probably write at s, x at s, like that. And then this is minus x alpha at 0, x at 0. And the whole thing has a 1 over s involved. Now, it may look like, oh, wait a minute, this is evaluated at s, this is evaluated at 0. You're doing things with tensors in different spaces. But these are just numbers, right? And we're just saying that this is the tensor's product, and the tensor sum, right? This is a tensor, that's a minus sign. Those are in the same tensor product space. Just so happens the numerical evaluation of this contraction, I can use the value of the tensors at s, and here I can use the value of the tensors at 0. Here I can use the value of the covector and vector at s, and here I can use the value of the covector and vector at gamma 0. So now we just take this limit as s approaches 0, right? Now we consider that as a limit. So if we consider that as a limit, we look at this expression and consider it as a limit, and this expression and consider it as a limit. So let's look at this one first. If we take s as a limit, we end up with the contraction of d by ds omega inverse x tensor product alpha evaluated at gamma s, and this is an s, right? Evaluated at s equals 0. That's what this whole thing is as a limit. The definition of what this is, right? It's a derivative with respect to x. Well, that has to be this thing, right? As you shrink x to 0, that's what this is the definition of the derivative of this term on the right side, right? So I now have the contraction of this derivative, right? And that I've just shown equals this thing. Well, what's this thing? Well, that's a function, and that's a function. So this is and this is 1 over s. This is the evaluation of the function at s at 0, at 1 over s, and as s goes to 0. Well, that's just the straightforward derivative of that function. And specifically because it's being evaluated as s goes to 0 along this curve gamma, right? It really is going to be the definition of taking the derivative along this curve, where every step of the way the vector along that curve, the tangent vector, is what we call gamma dot. So the right side of this curve, right, is it's ultimately well, what it ultimately is it's this times the function, some function which is defined by this thing in brackets here. So maybe the better way to look at it, because I'm having trouble pulling up the explanation very easily. Let me rewrite that as 1 over s. No, actually not 1 over s. Let me rewrite that as, I'm going to rewrite this expression here down here. And I'm going to write it as alpha x evaluated at gamma s minus alpha x evaluated at gamma 0 divided by s. That's a little bit easier to understand because now you see that this term here is being evaluated along the curve gamma s. So as s goes towards 0, this thing crawls along the curve from gamma s to gamma 0, and it kind of moves down this curve, and you're evaluating this expression at each point along this curve, right? And this guy here is just evaluated at this spot here, and s is essentially going from some number to 0, and that makes it easy to see that this is the covariant derivative in the direction of the tangent vector of this function, where is that? Of this function right here, right? That's because that's a function and that's a function. Well, that's a function and that's a number, right? So it's a function minus a number. But that thing here, that difference, is always going to be the contraction of x tensor product alpha, right? And so that shows us, now we just put these things together, right? This contraction here, by definition, is what this is, right here in the middle. And this combined with the derivative and the fact that you're evaluating it along this curve and that this is going to 0, that's what creates this structure here. And then this is the contraction operator. So ultimately, that guy dot contraction of x tensor product alpha equals the contraction along that curve of x tensor product alpha. And that shows that the commutator, or the contraction operator, and the partial derivative in the direction of our curve commute, right? So important point that those two things commute. Okay, so why have we done that? Well, what we're actually after is ironically, we're after a comp expression for alpha kappa delta. We're after the covariant derivative of one form alpha. We want that expression. We've already got an expression for the covariant derivative of a vector x delta, right? We know that. That's going to be x kappa partial delta plus gamma kappa alpha beta, not alpha beta, alpha delta x alpha, right? I think that's it. And so we want an equivalent expression for this guy, right? Now, spoiler alert, it involves a minus sign here and obvious rearrangement of the indices over here, but otherwise it's very similar. But we've got to prove it. We've got to get there. So that's kind of our goal, right? So with that in mind, we can get there almost entirely using a CFREE analysis based on just the algebra we've learned. So let's begin by taking the contraction of the covariant derivative in the direction of x of a tensor y alpha, like this, which we know is going to equal the we're going to use the Leibniz rule on the inside and then the linearity of the contraction, and we're going to get the contraction of the covariant derivative xy tensor product alpha plus y tensor product the covariant derivative of x of alpha, right? And we haven't explored this that much, right? We don't know much about the covariant derivative in the direction of x of a one form. We understand this guy real well, right? We can go into comp notation. If we had to go to comp notation right now, we would have no trouble except for this guy. But we know everything else. It's gonna turn out that we understand how to do the comp notation for everything except this. Well, that leaves us a hint of what to do. We expand this as much as we can. We put this on the left-hand side of an equation, then convert everything on the right-hand side to comp notation, and that will be the comp expression for this. So that's our strategy here. So we're just going to keep expanding like crazy, right? On this side over here, I can swap the contraction with the covariant derivative because we just proved that you could do that. So this is the covariant derivative with respect to x of the contraction of y contracted with alpha, like that, right? And that equals this side. Now the contraction on this side, the contraction of the sum of two tensors is the sum of the contractions. That's sort of an elementary fact about contractions. If you can prove that pretty simply, I won't do that proof here, but it's not too difficult to see. It's just a bunch of adding numbers, right? So this is going to be alpha covariant derivative of y. Remember, this guy here is still a vector, right? This is a 1-1 tensor, which in comp notation is y alpha delta, right? That's a 1-1 tensor. But when you contract that against x, you get that, and that contracts there, so you're left with one index, so it's a vector. So you have a vector and a one form, or a vector and a covector. So that equals that thing plus this guy, the covariant derivative with respect to x of alpha, oops, not tensor product, alpha, the covariant derivative with respect to x of alpha y. So we're counting on this guy to be a one form, right? Just like this is a vector, this has to be a one form. And the reason it has to be that way is the way we've defined contraction in CFREE notation, and the way we've proven. So we've proven that contraction commutes with covariant derivatives in certain directions. We've proven that the covariant derivative in the direction of x is a Leibniz thing, and we know that contraction is linear over the sums of tensors. So it must be that you have to be able to execute this contraction, and therefore that's the expression we're ultimately going to hunt down. We can also simplify this side, and we get the covariant derivative with respect to x of alpha on y. So now we have that equals this, and we're going to solve for this guy, right? So we solve for that guy, and we get, I'll have to rewrite it, I guess, covariant derivative with respect to x of alpha acting on y is going to be the covariant derivative with respect to x of alpha y minus the dual space mapping of alpha covariant derivative with respect to x of y. So we're getting close, right? We're slowly isolating this guy. He's still kind of trapped in this dual space mapping, but that's not too much of a problem. So what we'll do is we'll open up this dual space mapping, and we will start expressing things in comp notation. So now we're going to go into comp notation. So what about this? So let's start with this guy. This here is a function, right? So this is the covariant derivative in the direction x of a function. But we know that the covariant derivative in the direction x of a function is x operating on that function. So in this case, it would be x alpha partial alpha operating on the function alpha y, like that. But this function alpha y in comp notation is just alpha sigma y sigma. So alpha sigma y sigma is the function. So the partial derivative of that, I'm using alpha as a subscript and as the name of one form. I think you can deal with that. That is going to be x. Let me change it to beta. X beta alpha sigma y sigma, one line beta, like that, right? And that is going to equal x beta, and then we use the essentially the product rule, right? This is because that's a function of that is a function of space-time, and that's a function of space-time. So I will go with x beta times, it'll be alpha sigma beta y sigma plus alpha sigma y sigma beta, like that, right? So that can be that ultimately can be substituted for this and put right here. So let me do that. So it was x beta alpha sigma partial beta y sigma plus alpha sigma y sigma beta, like that. And then, so okay, so that's that term. Let me erase this so it's not too confusing. So that's what that term is. Nice thing about this being on YouTube is if you want to see what I'm erasing, you just back it up a little bit. And then we have to figure out this term. Well, we know that this first part here, right, that's just going to be x delta times y, excuse me, let's say y mu partial delta plus gamma gamma mu pi delta y pi, right? That's the literal translation of this expression into comp notation. But then we're taking the dual space mapping with alpha, so that will have. So the only thing that it's left after this contraction is, because this contracts here, that contracts there, the pi's contract, so you have mu. So what you're left with is you have to have an alpha mu, like that. So it's going to be minus alpha mu x delta y mu partial delta plus gamma mu pi delta y pi. All right, well, let me put this. So this expression equals this expression. So what are we going to do about this expression in comp notation? Well, we're going to have to break this down in the same way as we did with vectors. We're going to say this is x beta. Then we're going to define the covariant derivative to be alpha sigma partial double line beta, whatever that is, and it's got to contract with y sigma, like that. So now, we're trying to solve for this guy, right? We want to know how to write that in component notation, right? What is that thing? So let's look over here on this side, and what I notice is I've got alpha mu x delta y mu partial delta. So I have the x contracting with the delta and the mu contracting with the mu. And here I have x beta contracting with beta and y alpha sigma contracting with y. It's actually the same thing. If I just changed beta to delta in this, if I change beta to delta in this expression here, right, all the betas become deltas, then there would be x delta contracting with x delta just like it is here. And if I change the sigma to mu, then I would have mu contracting with mu here. And then this term and this term would be identical, and they're coming in at a different sign, so they cancel, right? So this term here cancels with this term here, and that leaves me on this side with x. Let's see, what did I said? I said I was going to change beta to delta, so it leaves me x delta alpha mu delta y mu minus alpha mu x delta times gamma mu pi delta y pi, right? And then on this side here, I'll just rewrite as x. I'll just do delta. I want it to be delta alpha mu beta y mu. Remember, they're dummy indices, right? Dummy indices I can rename to match, right? So I've got it all matching. I've got all the a's as mu's, I've got all the x's as deltas, and I've got y mu contracting here, and then this one has to be left alone as pi. There's no appropriate, because mu's already taken, right? Mu's already taken in this gamma index. It all keeps straight if you just follow those rules, right? The index gymnastics rules. So, but this has got to always be true for any vectors y and x, right? Any vector x and any vector y, you're going to have to get this to work. So I can actually take these vectors out. I can take x delta y mu alpha mu beta, right? Put it all on the left, and here I can take x delta y mu x delta y mu. Whoops. I want to change these guys, right? I want to change mu. I want to change mu into, say I'll switch mu to I'll switch mu to pi, and I'll switch pi to mu. Totally fair, because remember, dummy indices can be arbitrarily renamed, right? I want to do that. And that way I have an x delta y mu on both expressions, so I can pull them out, right? And that's alpha mu delta minus alpha pi gamma pi mu delta. Phew. Okay. Now this expression is supposed to be true for all values for all vectors x and y, right? This expression is true for all vectors of x and y, which allows me to write, this should be a double line here, right? A double line. I'm taking the double line from up here. It's the covariant derivative. Better neaten that up a little bit. Mu double line beta, like that. So therefore I get alpha mu double line beta is alpha mu single line delta. What didn't I do? Oh, I didn't change this beta to a delta, right? That beta should be a delta, right? Because if you look here, I switched that beta to a delta here to make everything match, but I forgot to change its paired up index below. I got the two sigmas right, but I forgot to change both of those deltas. So these have to match anyway. So you see, and I detect all these errors because the indices aren't matching, right? That's how you detect your mistakes. Like, wait a minute, the indices don't match. I must have left something out, and that's exactly what happens. It's a very self-correcting process if you do it reasonably slowly. which I'm probably not doing it nearly slowly enough, but then this is traditionally written with the gamma first, gamma pi mu delta alpha pi. And does everything work with the indices correctly? So I have a mu delta, mu delta, mu delta, that cancels. And this is your expression for the comp notation for the covariant derivative of a covector, right? And it's very similar to the vector. It's got the minus sign here, and of course you're doing the contraction up down that way instead of up down this way, because that's the only other alternative. All right, so now we understand how to write down the we now understand the idea of the covariant derivative of a vector, the covariant derivative of a one form, which we would also write in the comp notation, mu, say, delta, and alpha mu delta. We understand how these expressions connect with the ordinary partial derivative and the connection on the manifold. We understand how these are driven right into that. And this is the same thing, just sort of jammed into this coordinate-free notation, but it's really intended to mean the same thing as these two expressions. And so now that we can do it for a vector and for a covector, now the question is, can we do it for an arbitrary tensor Q? So it's where Q in the comp notation would be mu1 dot 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 mu p, nu1 dot 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 nu q. So it would be a p q rank tensor, right? And showing that will be our next lesson. See you then.